So I'd like to welcome today's speaker, Vitor Gulisz from Northeastern University, who's gonna give us a talk titled Representation Theory of Additive Categories. So thank you, Vitor, and you can start whenever you're ready.
Okay. Thank you very much for the invitation. It's a pleasure to be here. So yes, as the title says, we're going to talk about representation theory of additive categories. And the idea is that, well, we know that we have representation theory for rings for algebras. You take an algebra or a ring, and then you send the models over this ring or algebra. And then the idea is that, so we could think we could also do the same thing for categories, so for additive categories. So instead of rings or algebras, we could take additive category, and then we could try to get to study the modules over this category, and maybe use this approach to study the category that we started with. So in order for us to understand what a module over a category should be, let's first go back to modules over a ring, and let's see what they really are. So suppose we have a ring lambda. And then we put that. Okay, so what is a module over lambda? So we could say that a module, so let's say a right lambda module is, well, that should be in a Boolean group, let's call it M, such that you can multiply elements in the Boolean group by elements in the ring. It would be the assignment of in a Boolean group M together with multiplication by elements in lambda, and each multiplication is going to be, you can say that each multiplication is going to be a homomorphism from M to M. So it will be the assignment of an element group M together with homomorphisms, so group homomorphisms. That's called like this. So the multiplication by lambda, which will go from M to so basically, what we're doing is we start with the ring lambda. Then we assign this to this ring in a Boolean group M, together with these homomorphisms for each element of lambda. So we have many homomorphisms here. And these homomorphisms, they should satisfy some properties, of course. So the properties that we need to define for this to be a module over lambda. And the properties will be the following. Okay, so it's an assignment, blah, blah, blah. So we set that. So first thing would be that if you multiply so if you multiply by lambda 2 first, and then if you multiply by lambda 1 later, they should be the same as multiplying by lambda 2, lambda 1. And also we know that the multiplication by elements of the ring, they should be it should distribute over the addition, which means that I can see that if you take if you multiply by lambda 1, and if you multiply there by lambda 2, and if you add those two things, this would be the same thing as multiplying by the sum of them. And also the third condition is that if you multiply by 1 by the unit in lambda, it's just going to be that is the number. So what are the conditions that we need? And so we should have an abelian group and with those maps satisfy all the structures, so that's going to be a model, a right model over lambda. And now there's something that we can note here that this looks very much like a functor, like an additive, naturally a contravariant functor, because we have this. So a functor should, so a contravariant functor should respect the compositions, but this is going to flip, so it should be contravariant. It should send the identity to the identity. And because we have this also happening, it should be somehow an additive functor. So we see that there should be an additive contravariant functor that should be defining all of this. So that's the idea. And now we can try to make this precise. So how can we define a functor from this? So we already saw that we have somehow an assignment from lambda to this. And this assignment is given by this, which so it seems that this assignment should be a functor, an additive functor. Now, to make this precise, we need to have categories. So on the right side, we could say that we are leaning in the category of abelian groups. But on the left side, we also need a category. And we can do that. So actually, we can see lambda, the ring lambda, as an additive category with a single object. And by doing that, we can then make this precise and say that indeed we have a functor. So what we can do is that we can regard lambda as a category. So let me write here. That would be a reality, but it means that we can basically add more business. That's all this category of big lambda. So this category is going to have only one object, a single object. Let's say X. And so, and what are the morphisms in this category? They are going to be the elements of the black morphisms from X to X, which is the only object in the category, is going to be lambda. So set. And then we define what is the composition in this category. We take two morphisms in this category, which are just two elements of the ring. We define the composition to be the multiplication in lambda. And then we also know that this is equal to lambda, so in particular it is an abelian group with the addition. So this also is going to imply that A lambda is an additive category. Sorry, a pre-additive category. There's can add morphisms, and this is going to be an abelian group. It's also going to distribute over the composition because we have a ring. And now we can say that what we have here is actually a functor. Because then we can define a functor F from this category A1 to the categories AB of forbidden groups by setting f of x equals the group M and f of lambda equals this morphism set. So if you do this, so this is going to be a functor by all the properties that I've seen. It's going to be also a additive functor. So what happens is that, okay, so let's just rewrite this picture. So we have a lambda, then we have the morphisms, and now we have a functor. And this will be a contravariant functor. So we should have so this is the category A lambda. And now here we have f of a lambda by the category AB of forbidden groups. So what I'm seeing is that a model is just a functor. And now, once we know that, we can then see other case because okay, so a model is a functor. A functor will be a way to represent the ring as in the category of forbidden groups. But now being a functor from a pre-additive category to the category AB, we can now just take instead of A lambda, we can take any pre-additive category, let's say C, and then try to do something similar to represent the category in the category of forbidden groups. So now let's say that we have a pre-additive category C. So now maybe we can try to imagine that C will have some objects. We have many objects and morphisms between them. And now we consider this out. If we take a functor from C to the category AB of forbidden groups. So we can think that, okay, so a functor is going basically to take each object and send to an forbidden group. And it's also going to send the morphisms to morphisms of forbidden groups, and everything should respect the properties of C. So basically, we're going somehow to represent the category C in the category of forbidden groups. Let's say we have a contravariant functor. This would be so once we have this intuition that a functor is going to represent the category, we can then define a functor like this to be a model over C. So a model, so a right C model. So this is going to be the definition is contravariant additive functor from C to And then we also have the category of C models, right C models. For the objects, I chose these C models, the functions, and the morphisms between them are the category transformations. So this would be a category. And then we can now use this category and the C models to try to understand the category C. And actually, this also recovers the case of models over a ring because we have the when we take mod over a lambda. So this category is going to be isomorphic, not just equivalent, but isomorphic to the category of models over lambda. So there is an isomorphism of categories. We just take a function here and evaluate itself as. Now to take another transformation and evaluate at max. So indeed we can do all of this and we recover the case of models over a ring. So that's good. And okay, so basically the idea is that we saw that models are functors, and we also say that functors are models. So we should think that they are the same thing. Now, to get some intuition about what's going to happen here, let's see what happens with the unit dilemma when we think about all of this. The unit dilemma basically says that if you take the collection of natural transformations between representable functor and functor f, let's say that f is an additive functor. So f would be a additive multivariate functor, so it would be a C model. And so it says that we have isomorphism from here to f of x, which take that into summation, evaluates at x, apply it to what? To the of x. And so this is going to be an isomorphism, which is natural in both x and f. Okay, we know that we have this. Let's see what happens when the case that the category C is the category A lambda. So oops. Now, because we know that we have the as a works of categories of here, which is just evaluating an x. This x side is going to be isomorphic to after just consider x. And now if we remember that a lambda x is just the ring lambda. And we can call fx m just to get it better. take the entry here. So this diagram to compute, and then this is just going to take. So remember, this map is going to take at essential at x applied at 1. Here we already have at measured by x. All this f maybe. And this is just going to send f evaluated as 1. And it is going to be an isomorphism, which is just the isomorphism that we know from basic theory from models of our ring. But the point is that the unit dilemma restricted to the state of models of a ring is just this classical isomorphism that we already know. So we can think that somehow the unit dilemma is generalized this isomorphism. And we can make it a little bit more precise if we think the following. In this case, we saw that, okay, so this functor here, which is the representable functor by x, it corresponds to this, which is this lambda. So somehow the representable functor is going to be the ring lambda. And by taking x and sending x to the representable functor is a way for you to regard your ring as a model over lambda. And now here we also have something similar. We also can take x and send to this functor. That's just the unit embedding. So this is going to give us a way to see the category C inside the category of C. So it's somehow a way of seeing C as a model of your C. It's not very precise, but what's happening here is the same as I said before, that when we can have ring lambda and we see lambda as a model over lambda, here we have the same thing happening, but it's just that we might have many objects, not just one object X. So this gives this is going to be a fully faithful embedding. And so this actually allows us to see C inside the category of C as this things. So when we go back to this isomorphism here from the unit dilemma, we can think somehow that what's happening here is that we have this on C is isomorphic to them. So this is a way we can think about the unit dilemma. The equation is just that this is just the general case of this isomorphism. Okay. Now, for the rest of the talk, let's assume that C is going to be an additive factor, which is also idempotent. and then details what idempotent complete means, but basically just means that, so this is an additive category, and basically being idempotent complete means that it has all of its possible direct sums. So that's the idea. But an additive category that if you know that this category has a direct sum, it should also be in the category C. And the idea is that we're going to take some category like this, and now we would like to use models over C, so models over this category to understand this category C. And before we see some a few things we can get by doing that, let's see some examples of what would be the same. So, examples of what we could consider. We could consider any abelian category. So every abelian category is additive and idempotent complete. We can take an abelian category that's null to be category C. You can take any additive category with kernels or co-kernels. So if that category is additive and has kernels, it's going to be idempotent complete, or if it's additive and has co-kernels, it's also going to be idempotent complete. And for example, you can take if you take, for example, let's say that A is an abelian category, and then you take the category of short exact sequence over A. So the objects are the short exact sequence, and orphans are just the maps that makes everything commute. This is going to be an additive category that has both kernels and co-kernels, so that would be an example. We also have other examples coming from functional analysis. For example, we can take the category of Bunny space. Can take, for example, the category of normed space. Or even we can take PDS, the category of homological vector space. All these categories are going to be additive with kernels and co-kernels, so they will be idempotent. So those are all possibilities that you can take for C. And of course, there are many other possibilities. In general, if you just take, if you start with any of these categories, then if you take a solid category which is closed under direct sums and direct sums, this is also going to be additive and idempotent complete. So there are many, many possibilities that you can take for C. And then hopefully you can use all these ideas of models over this category to study this category. So let's say you want to study Banach space. One possible approach would be, okay, so let's take the models over this category and let's see what we can what we can get. That would be one. Now let's go back again to the general case, and let's just give a few definitions. So let's see. Let that be a C model. So we say that F is finitely generated. So for the case of a model programming, a model is finitely generated if there is a dimorphism from copies of lambda to this model. And now we're going to say that F is finitely generated if there is an dimorphism this for some X in C. And then they're also going to say that F is bit. So for that. From this, we see that we can see that the category approach C finitely generated projective model. It will be actually you can start with the representable functors. All functors that are isomorphic to something like this. And by using the unit embedding, we can actually conclude that the representable functors, this category is equivalent to the category C. So basically, we have that this category is equivalent to C. So in a way, we see that the category C is going to correspond to the finitely generated project objects, this category of models over C. So it's a very nice way. So we start with the category C and then we make it projective somehow. Now we're going to say that F is finitely presented if there is an exact sequence of this form. First one X was, and this is the same as when the finite presented model for array. So this is the same definition. And we are going to denote the category of finitely presented models as mod C with small m. So this will be category of finitely presented C models. And actually, this is the category that we're going to use mostly to study C. So what we're going to see next is how we can describe properties of the category C in terms of this category mod C. Now the goal is to describe properties.
Could you change the pen?
Yes. So the first thing that we can say, very basic one, is that the category C has weak terms. Which means that every morphism in this category has a weak term, and the baseline weak term is just almost the same definition as a kernel, but the difference is that so when you define a kernel, you need a morphism satisfies some universal properties, so such that every other morphism with the position zero should factor uniquely. If you remove the uniqueness part here, this will be the definition of a wiki kernel. And C has wiki kernels if and only if this category mod C is additive. So this is the first instance that we see of how we can describe the property of C in terms of mod C. Now we can go a little bit further and say that C has kernels if and only if mod C is additive. And the global dimension of this category is at most 2.
So if we have only weak kernels, do we have a like a bound for the global dimension of the category? It could be infinite.
Okay.
Okay.
We will also, so let's assume that let us assume that mod C is additive, so let's assume that C has weak kernels. Then we can also prove that in this case, every monomorphism in C is a kernel if and only if every object in mod C that dimension at most 1 is a CDG. That's being a CDG just means that it embeds each object. So there's a monomorphism from this object to a project. Also, so note that these conditions that having kernels and this that every mono is a kernel, those are conditions that you need to ask to define an abelian category. And somehow now we are translating these properties in terms of mod C. And actually, by taking opposite categories, we can also get the dual notion. So for example, that C has 4 kernels, we have to be written on it, mod C op. So models over C up would be abelian and with global dimension at most true. And here also that every co-kernel is a, so every eight is a co-kernel, eight and on it, every F mod C up with correct dimension at most one is a C. With this, you can take a result that characterizes abelian categories in terms of models over C.
Each of the good kernels have a finite bound, for instance, on the amount of factorizations. Can we get a conclusion of the dimension of
If you had a bound where?
on the amount of maximum amount of factorizations of each week. For example, say there are not two morphisms that factor.
That's a good question. I don't know. I don't know what to say about it. I have a feeling that we might not have that. Because I guess if you have more than one, maybe you should have, in those cases, we have infinity many possibilities. I don't know. But that's interesting. So if you combine this thing that we have seen so far, and now state the following region. Still be a billion call. C is a billion, it only has kernels, it has co-kernels, every model is a kernel, and every eight is a co-kernel. And now we know what those conditions mean. So we just need this, and the two. So let's just write them here. So it should satisfy the following actions. So this one. And then after the go with go action. So mod C up. In models over the opposite category, you can think that although they're going to be covariant functions, and then you can think that those would be the F models. So now they should be abelian as well. The global dimension. At most two. Now the condition that every model is a kernel. It corresponds to this. And we do that every eight is a co-kernel with this. Do the same thing, just change this for C on. Okay. Before we make some further comments on this, let me also say that we also have some other things that we can do on the side by describing properties of C in terms of model. Something else that we can do is that if you assume assuming that C is a billion, we can prove that category C has enough injectives if and only if something happens here. So that's if only the dominant dimension of the category must be at this point. And the dominant dimension of the category is just a homological dimension, which takes into account projected and injected objects. We're not entering details here, but basically we can then characterize now another property of C in terms of a homological condition for the category model. And in the case where C is a billion and C has enough injectives, actually this dominant dimension is going to be at least 2. And you can actually use this condition to give another equivalent way of characterizing when a category is a billion with enough injectives. So now we also have the following result. And that will say is a billion. And has enough injectives. Now we can assume that both mod C and mod C of are leading. So that C has weak kernels and weak kernels. And with all conditions that the global dimension of mod C is at most 2, and the dominant dimension is at least 1. That would be another way to characterize a category study with enough objectives in terms of homological conditions for the category modes. Now, when you look at these two results, it's very interesting to note how the condition of the category being a billion, so a billion here and a billion with enough injectives, they depend on these numbers 2, 2, 1, 1, and also 2. So somehow you're parameterizing the property of the category is a billion in terms of a number. And now, so once we have this, we can think, okay, so why did they change these numbers? Are we going to get anything interesting there? And okay, so and then we could ask, okay, how should we change these numbers? Because there are many possibilities, right? We could take many options for these numbers and these numbers here. And one possibility is the following. If you know that Q is 1 plus 1, right? We can then now change this number 2 to anything like n plus 1. N plus 1. And here instead of 1, we're going to put m. M. And by doing that, we can then define and in a given category. Where n is a positive integer. It will be any additive and added polynomial category satisfy these conditions now for n plus 1, n plus 1, n. So we could do that, and actually, it turns out that by doing this, we did get the notion of the n-abelian category, which is something that has been defined a few years ago, and people have been studying, which is part of something that we call higher homological algebra. And actually, it turns out that, okay, so the definition that was given by Gustavo Faso about 10 years ago was not this way that we defined. Actually, it took the axioms of an abelian category and then it generalized these axioms to something longer, and with these generalizations, he defined an abelian category. But now we can see that this generalization just corresponds to change these numbers here, these axioms, by taking n plus 1 and plus 1 n. And also, when you do that, you can also change this number 2 to n plus 1. And the result is also going to move. So C is n abelian and has enough injected C common with these two are abelian. And the global dimension of this is set most n plus 1 and the dominant dimension of this n plus 1. So everything is going to work there. And the point is that, okay, so we see that the use of studying models over the category C is that it gives a very powerful way of visualizing properties of the category C. And it gives, maybe I would say, a clear perspective of what, for example, the notion of an abelian category is. Because when the definition of the n-abelian category was given, it was based on an attempt to generalize the axioms, and which was a good attempt, so that is very successful. But using this perspective, you can see that, okay, so this makes a lot of sense. We are just changing the numbers there in the parameterization. How much time do we have?
10, 15 minutes.
Okay. So I think it's a very nice application of the use of models over the category. So in general, we could now try to go further and then replace the properties of C and then try to see how we can describe this problem in terms of mod C. Then really we can also use mod C to work in this context and then to get properties back to mod C, to C. And as I said before, we have many examples. Well, here we have many possible examples of category C that we can take. And we could also take any specific example and try to study the models over this example, over this category, and see if we can get anything interesting that's going to help us to understand the category C. And one case that was very successful this direction was done by Alexander and Brighton. This is how actually they got the notion of an almost fit sequence, which is some kind of short exact sequence, which is very important in the representation theory of finite dimensional algebras. So I just want to finish by saying how they got this notion of almost split sequence by studying this capital mod C. So let's take equals mod A, where A is finite dimensional algebra. Okay, so we start with the finite dimensional algebra. Then we want to study this algebra. One way of doing that would be by studying models over this algebra. So by studying the category model. So now you shift the problem from the algebra to the problem of studying this category of models over here. Now you have a category, an additive category, and you want to study this category. So now you can go one step further and study the models over this category. So the models over it. So we could study mod A. And hereby small m, I mean the finite dimensional models over it. So following these ideas, that's what we should do. We should study models over this category, models over it. How often finitely presented. And so what Ausländer and Wright did that was in the 70s. So they thought, okay, let's study the models of remote data. And what they did was they proved that the simple models of remote data, so the simple functors, let's say like this, they proved that the simple functors, they are finitely present. And a simple model over C, so a simple functor is just, it's the same definition as you have for models over a ring. It's a model over C, which is non-zero, and for which the only set the objects are just a zero object and itself. This would be a simple C model. So what they prove is that every simple mod A model is finitely present.
Is this due to the fact that mod A is confinite? Or not necessarily? It's more involved than this.
This well, this is very important, but we need actually something more. We actually did the duality. We need to do the duality from mod A to mod A.
Okay.
That's this actually we went to doing this. Okay, so they proved this. And okay, so now let's take S should be a simple model, so a simple mod A model. So because of this, we have that S is in this category here, finally presented model over mod A. And now being finally presented in this category. So sorry, so because this in this category. and you can actually conclude. Okay, so this category is going to be an abelian category because, well, mod A is abelian. So mod A is C in this case, right? So we know that mod A will be abelian with global dimension at most 2 and now those other conditions. And the projected objects in this category here are given by the representable functors. And also because mod A is a Proof-Schmidt category, which means that every object can be decomposed as a finite sum of the composable objects with local endomorphism ring. You can take projected colors in this category. So in the end, you can actually get a minimal projected resolution of S inside this category. So let's do that. So because this category has global dimension at most 2, we should sequence like this. And so this morphism, for example, is a natural transformation between this representable and this representable. But the unit dilemma is actually induced by a morphism from X to Y, and also this will be induced by a morphism, say G from Y to Z. So by taking this minimal product resolution, we get these two morphisms. So we're going to get this sequence here, X, Y, Z. We associated this to the symbol functor S. So in a way, we can take a simple model, and then for each simple model, we get a unique sequence in the category mod A, and it's unique because minimal project resolutions are unique. And then what observed and driving the truth is actually that this sequence that we're going to get, they are actually very interesting, very important. So if we assume that this is non-zero, which means that S has a dimension equals to 2, then actually this will be a short exact sequence. And both X and Z are going to be decomposed. But in some way, the simple functors are going to give us, by doing all of this, they will give us this short exact sequence, which begin in the decomposable and end in the decomposable. And those sequences, they were called by Alexander and Vitor almost straight sequence. So they're called almost straight sequences. And yes, indeed, they don't flip, but somehow they are very close up in space, so somehow they are minimal with respect to splitting in some sense. And actually, There's a whole theory that you can get by studying this short design sequence, this almost sequence. That's part of what we call nowadays Ausländer random theory, which plays a very huge role in the representation theory of models over finite dimensional algebra, or more generally over an arcing algebra. And it's very interesting to know how all this, so how this huge theory that we have nowadays came from a very simple naive question, which was, okay, let's take a simple function and take a minimal project resolution. We get some sequence which should be meaningful somehow, and actually they are very meaningful. So the point is that by studying models of our categories, we can get some very interesting concepts that that might be very important. And essentially, studying models of our category, they give us a different perspective of how approach things that we, otherwise we could not see, or otherwise that would be very hard to see.
Mm.
And the idea, okay, so this was the case when the category C was not big. We have, of course, many other possibilities for C that we could take. And it could also be, okay, let's take each be some of these categories, for example, and let's try to study the models of this category and see what can happen, and then we can get something interesting. The same way that Ausländer and Wright developed this huge theory by just doing some very simple questions regarding models over this category. Oh, that's all I have to say. Thank you very much.
Thank you very much. It was a very nice talk. Are there any questions?
So before going to the questions, actually, I would like to make a remark because Vitor has been very humble. And actually, so these two theorems with the ends are Vitor's results. I mean, this is part of his PhD thesis. And these are very, very important and very meaningful results, I think. I mean, give a complete new perspective in higher homological algebra is something that, as he has mentioned a bit, has been a central topic in representation theory of arcing algebras for the last 10 years. So yeah, this is a very, very nice results, and I would like to emphasize that because it's worth noting. And now I come to some questions. So, okay, you have all this. You said that then you need to have the duality to have enough injectives. So you, by definition, mod C would have enough projective, right? I mean, because you're taking only finally presented objects.
Yes.
So enough injectives, how do they?
Well, I can say that in this case, the case in the assumption of this result, the category mod C has enough injectives.
Right.
At least in this case, I know that this will happen. But marginally, I don't really know.
Okay. Right. And more coming a bit back to your own results. So you have so there is all this theory of Ausländer-Reiter, and there were some almost split sequences in higher homological algebra. You recovered those those results as well.
Exactly, yes. So there you take n plus so the category of mod A to the C. And you do the same thing, you can prove that it's simple factors on part of the set, and then you take again linear project resolution of S, now it's going to take a little bit longer. And you get again sequence of morphisms, and this sequence that you get, they are actually n almost split sequence. So
Right.
we have exactly the same thing happen.
Right. I do have another question. Yeah, so all right. Then I would ask in private.
Okay.
Any other questions? All right, let's thank Victor again.